Thank you for joining the Using Advanced PBR Material Parameters in glTF webinar. During the webinar, members of the 3D Formats Working Group will give updates on the latest PBR extensions. Leading today's webinar is Ed Mackey from Analytical Graphics and Chair of the PBR Task Subgroup. Ed?
Thanks, Jeff. Okay, I'll get this started here. So today we're going to do a quick overview of the PBR model, that is the physically based rendered material model that we ship with glTF. I'm going to spend about 20 minutes on that overview, maybe a little longer, depending how things go. And then Alex Wood is going to give us a quick tour of the real-time implementation of transmission in PBR. So covering some of the more recent, more advanced PBR materials and how you'd implement them in a rasterizer. And after that, we have an expert panel here. These are folks who've been deeply involved in inventing, designing, and specifying all of the PBR parameters that we're going to show today. And they're here to answer your toughest and most challenging PBR questions. So I hope you came prepared with some deep PBR questions to ask those people. If you do have such questions, please use the Q&A feature of Zoom. There's a separate chat feature from Q&A, and if you ask questions in the Q&A, it lets our moderators here keep track of each question individually and mark it as answered and all that. If you drop your question in chat, it may get lost. We are also recording this. Hello to everyone watching the recording later. That's going to be up on YouTube and available from the Kronos website afterwards. And if you don't mind, Kronos hopes that you will fill out a survey to let us know how we did with presenting this material at the end. So let's dive right in. Quick reminder of what glTF is. Obviously a 3D model file format. It is a format that is specifically tailored to be the end product. It is for last mile delivery. So when you're first building an asset or designing a 3D model, you might be saving it as a Blender save file, or you might be saving a set of USD files as you're working with the different art assets. And then when you're done with it, you publish to glTF. The act of publishing it to glTF changes the nature of the data that's stored. It's no longer organized the way it would be for an artist to continue editing the model. And instead, it's packed in more closer to the way that a consumer GPU would need to render that data more immediately. And that has implications for our material model. We don't necessarily want your average glTF file to have a fancy Material X set of 1,000 shader nodes and then deliver that onto some mobile phone with some battery operated GPU and ask it to render such a sophisticated shader. We can get in trouble that way very quickly. So we have a set of parameters, PBR parameters, that can be organized into, some people call it an Uber shader, but it can be sort of a fine-tuned shader that can be tailored to each application or each platform and really target that platform well, and yet remain compatible with a wide array of physical materials. So how do we come up with these parameters? Well, Kronos maintains a PBR subgroup, the PBR TSG, or task subgroup, as we call it. I'm the chair of that group currently. We work underneath another group within Kronos called the 3D Formats Working Group. And that is the group in charge of glTF itself and a few other standards like KTX2. But our charter in the TSG underneath that is just to focus on the PBR materials for glTF. Well, physically based rendering in general for glTF. Primarily what we've done so far is those materials. We meet every Monday. It's a fun meeting. We like to have cool 3D graphics demos and stuff. All of these logos that you see here on the slide, these are all member companies within Kronos. The subset of members that I'm showing here are members that usually contribute 1 to 2 employees every Monday to our meeting. If you're a Kronos member, please, you're welcome to come join us at these meetings. or join Chronos and join the meetings. If you're not able to do that, we do also have a public repository, the main glTF repository on GitHub. Almost all of our drafts appear as public drafts as pull requests in that repository, and you can leave public comment and feedback there as well. The meetings are more lively and interactive, though, I will say that. So let's talk about our approach to defining PBR materials. It's an extensible set of parameters based on physical properties of real materials. It sounds so mechanical and boring when I just read that off the slide like that, right? But it is really based on these physical properties for a reason. And to highlight that, I would bring up one example. We had an example recently of a proposal for a subsurface scattering algorithm that seemed really cool. It was a very popular algorithm used in a big game engine. It had these 4 different input parameters that were sort of artist knobs that could be played with to get a cool real-time effect. They weren't based on real-world materials at all. It was just fudge factors for this particular algorithm. And we're not able to take a proposal like that and incorporate it directly into glTF. Because if we did, then the material model of glTF would be hooked inextricably to that one rendering algorithm, and you wouldn't be able to use it with anything else. So we don't want that. We want parameters that are based on actual objects' properties that can make sense to all sorts of different rendering engines and architectures. We want them to be useful in path tracing and ray tracing and rasterization. Sometimes we have the occasional helper parameter to help the rasterizers along when they can't do all the fanciness of the path tracing. But beyond that, the core important parameters all need to be physically based. And to that end, we don't even claim to have a reference viewer. Reference is a word with a special meaning to a standards body. It means the truth, the only correct way to do it. So we don't make a reference viewer. We ended up renaming that thing our sample viewer. And we did that in order to say that real life is our reference. So our material property is based on some actual thing that you can measure in the real world. And if you take a picture of it in real life, that's your reference. Real life is your reference. So for example, on the slide here, we see an iridescent lamp from Wayfair. They contributed this as a glTF model, and they also have reference photography on the left there. And you can compare the model to the photography and see how close we came. So that's our approach to defining these parameters. What about extending? So glTF 2.0, the most recent version, was released in 2017, several years ago now. The core of it is set in stone, right? We don't change the core glTF. The only way to add new things into it is with glTF's built-in extension mechanism. So all of these properties we're showing today, they all count as glTF extensions. In fact, we spend our call on Mondays talking about glTF extensions because that's how you get new parameters injected into the standard. But that's not how we think of our material model. The new properties are all core parts of the material model, even though architecturally they end up as extensions in the JSON of the glTF. So for example, here I've got screenshots of both Blender and of 3D Studio Max, and we're seeing in particular the glTF material node that was recently added to 3ds Max. And it's got sheen, it's got transmission, it's got clear coat. It's got a number of things that we consider glTF extensions, but they're a core piece of that material model. And even if you load a simple red cube from glTF, you still see those options showing up. You didn't have to do some extra thing to make that appear. They're part of that model already. So some of these PBR extensions, as I will continue calling them, add an extra layer. So on this slide, we're seeing iridescence, sheen, and clear coat. These are 3 extensions that add an extra layer on top of a base material. And iridescence is our most recent one. It was released earlier this year. It has the interesting property that the layer of film that it adds is so thin, it's on the order of hundreds of nanometers thin, and it causes light to interfere with itself when it reflects off of the top versus the bottom of that thin layer, like an oily substance almost. It produces this sort of rainbow pattern of colors that you wouldn't otherwise get from the material itself, which is kind of a cool effect. So alpha blending. Everyone knows about alpha blending, right? So glTF, though, takes the strategy of specifically saying that alpha blending is coverage. Now, coverage is an important concept for us. It means in this case, it's alpha blending is indicating whether the material is present or not. So, for example, you might have a quad with a set of green pine needles on it, and there may be gaps between the pine needles where the green material is missing, and the alpha values can be 0 there to indicate that the material is completely missing from those places. But you may also find fractional alpha values and wonder to yourself, well, how can it be a percentage when it was a yes or no question whether the material is there or not? Turns out if you zoom in on those individual pixels of the texture map, you will see they take up a small but finite amount of surface area. So the one I'm indicating with my lower blue arrow on the screen, that one pixel is not a single point. About 40% of it is being covered by a green pine needle laying across it, and the other 60% is air. There's no material there. So it has a 40% alpha value there. So coverage is a concept you'll see repeated a lot, the presence of iridescence, the presence of clear coat, even whether the material is made of metal, the metallic value. Normally it's yes or no. Is it metallic? Is it not? But you can see a percentage on some pixels because of this concept of coverage. Some percent of it is metal and the other percent is rust or something, and you'll get a fractional value. But you do not use alpha in glTF for glass or water. Those materials are fully present, so you don't need any strange alpha values there. You get them 100% alpha with no blending, and instead you use something called transmission. Transmission was added a couple of years ago to glTF. It specifies that even when the material is fully there, it allows some light to pass through. And the light that passes through still is subject to the material being there. It can still have a Fresnel effect around the edge. It can still have specular reflections on it. It lets you know that there's glass or water or some sort of material there. It requires a very different rendering strategy than what we use for alpha blending. And Alex is going to explain that in a little more detail in the next section. And it has two different modes. It has a thin-walled mode, which is our default mode, and it has a volumetric mode with our new volume extension. So thin-walled mode is shown in both these screenshots, actually, but especially the lower one I want to draw your attention to. It's a yellow sphere, but it's in thin-walled mode. So this is not a solid yellow marble. This is more like a bubble of glass. Imagine like a low poly car. This might be the windshield of the car. It's not filled with glass because it's in thin-wall mode. And you'll notice this produces some interesting effects. When the glass is rough, it can blur what's behind it. But if you look at the grid lines cutting through, you won't see some massive distortion the way you would with a solid marble. The refraction isn't doing the thing you might expect from looking at a solid marble. So let's talk about index of refraction because there's some interesting effects there. So here in my diagram on the left, I'm showing a case where we have a thick piece of glass in a special case where the front and back surfaces happen to be parallel. And something interesting happens to the refraction math in this case. In yellow, we see a ray of light coming along and striking the glass at an angle, and it refracts. It changes its angle and goes across the interior of the volume of material. And when it's done that, it hits the back side. If the back side happens to be parallel to the original, then that same mathematical formula plays out in reverse, and the light refracts again, placed back on a path that is parallel to the original path. So the ray of light becomes offset, but is not sent away in a new direction. And that is a special case of this being parallel like this. So in the diagram on the right, we see what the implication of this is for a thin-walled material. The blue line here represents one polygon seen edge on, so it's infinitely thin. And the yellow line, again, is a ray of light striking that glass polygon. It refracts, but it undoes that refraction in the same location. And it ends up continuing on as if nothing had happened because the material is so thin, you can't discern from where it refracted and where it exited the material. So it's tempting to say, well, refraction has no effect for thin-walled materials. That's not entirely true. You remember that blurring we saw in that photograph. So let's zoom in. This is my diagram. I'm attempting to zoom in on a thin-walled material here. The squiggly blue line, once again, represents a single polygon seen on edge. But this time, I've zoomed in far enough. I'm attempting to show the roughness. So this is a piece of glass with some roughness applied, and that creates these things called microfacets on both the front and the back of a thin-walled material. And I've drawn them a little exaggerated in size. In reality, there would be many, many of these. They would be really tiny. But I'm showing them magnified here. And you'll notice that we don't assume that the front and back of these little microfacets are parallel in any way. So 1 pixel's worth of light path can strike this thing and get scattered in all different directions. And that creates that frosted glass effect, the blurring effect. So even though you don't see what I guess I'll call macroscopic refraction, you still get this blurring effect from the microfacet refraction that's happening there. And it's interesting to me that this happens as a consequence not just of roughness, but of IOR as well. If the index of refraction were 1.0 for this blue material, then any amount of roughness would be unable to perturb the light going through. And vice versa, if this thing were made of diamond, then even a tiny amount of roughness would send this light scattering in all directions. But enough about thin-walled. Let's talk about our other mode, which is volumetric rendering mode. This is turned on with the KHR materials volume extension. But as with all of our extensions, it does not matter whether the extension itself is present or not. It matters what parameters are being carried by that extension. And in this case, there's a parameter called thickness factor. And when thickness factor is non-zero, that indicates that that entire material and all the meshes using that material have exited thin wall mode and are now in volumetric mode. This changes the assumption for your polygon mesh. Your polygon mesh in thin walled is assumed to be a loose collection of triangles, each one of which is a perfectly thin little piece of material. But in volumetric mode, your polygon mesh instead is expected to be watertight. It is a manifold mesh wrapping around some three-dimensional solid volume of material of any shape. And it doesn't need to be parallel on the front and back or anything like that, as long as it's watertight. It's hard for rasterizers to deal with such things, but we do offer a thickness texture map. That's a texture map that indicates the average thickness at any average depth at any point along the surface, and that lets you approximate the thickness. And that can be important. For example, the screenshot here, we're seeing a material that absorbs some light as the light goes through, and it turns a deeper shade of blue. It has a blue attenuation color. And the further it travels through the material, the bluer it gets. So we use the thickness map to emulate that in real time. Path tracers are free to ignore the thickness texture map. They use their normal path tracing to calculate those distances traveled through the solid material. But at the same time, they still must test that thickness factor initially just to see if the entire material is in thin walled mode or not. And once they know it's volumetric, they do their normal path tracing thing. So we do have some extensions that are still on the drafting board. This is one called diffuse transmission. This is, you've heard of subsurface scattering. This is sort of a surface level scattering event that happens. It can happen in thin walled mode, and we implement it by having the diffuse lobe transmit through the material instead of the specular lobe, as with our original one. And so it can be used for something like a leaf, a blade of grass, any sort of thin material that completely scatters the light on its way through, even if the surface of that leaf might be smooth or might have smooth and rough patches. The light being transmitted through is always completely blurred because it's the diffuse lobe coming through. So here, these are just photos. I took some reference photography. We don't have samples for this. It's still on the drawing board. But I imagine that this is a plant. It's an angel wing begonia, if you're curious, that my mother grew. And it's, so on the screenshot on the right, we see what I think might be its base color, which is green with white spots. On the left, we see what's happening inside or on the back of the leaf, which is a set of red veins. And then in the center, I'm showing what happens when sunlight filters through the leaf. So if this leaf were on a quad, you would want that base color with green and white, and then you'd want a diffuse transmission color with a set of red veins. And in theory, you would get that effect coming through. So that's the thin-walled mode of diffuse transmission. We also have another extension, subsurface scattering. So if you recall, our default glTF material is opaque. So to allow any light into a 3D volume of material, you need one of the transmission extensions, either the original one or the diffuse transmission one, which I just showed you. Subsurface then has these dependencies. It depends on volume, which in turn depends, in this case, on the diffuse transmission. There are cases where you might use the regular transmission, but I'm not going to get into that for today. So you see the sort of the ideal subsurface workflow here. Down at the bottom of this diagram, you have a scatter color and a scatter distance that are provided by that SSS extension. Those are true volumetric properties. They're untexturable because they're happening inside this 3D volume of material. But at the surface, we have our diffuse transmission, which is that extra scattering event right at the surface. And that lets you place a texture down because that is a surface property. And you can control that diffuse transmission color with a normal UV atlas, just textured across the surface in that way. So I've showed you a bunch of extensions with a bunch of different dependencies and relationships. I ended up creating this diagram just for our group to try and get this all straight in our heads. We have these different vertical swim lanes where the artist might want transmission or SSS or refraction. And this sort of is the cheat sheet showing, okay, which extensions do you need and how do they work together to produce that effect that you're looking for. And these slides are going to be available after the fact, so you may examine that in more detail at your leisure. But let's talk about how we author these things. There are many pieces of software that are adding support or have added support for our newer PBR extensions in glTF. Notably, just 2 weeks ago now, Blender 3.3 shipped. And this particular version of Blender has upgraded support in it for a number of these extensions that I've shown off today, not counting the draft ones. And it will let you do all the volume and transmission and those kind of extensions that I've shown here. Autodesk, I mentioned before, they've added a glTF material node to their material system. So you have a full implementation of that material model as a single node in their system. UX3D has a product called Gestalter. They can take a finished glTF and hand tweak. They provide a user interface to edit those PBR values and apply the PBR extensions to it. Kronos has our glTF validator. It's been upgraded with support for finding common problems in the usage of these PBR extensions. My own little pet project, the glTF tools extension for VS Code, has some upgraded support there. And Material X has a new node. So let's talk about Material X for a minute. Material X has a new glTF_PBR node that's been added to it that actually shipped with the stable version 1.38.4 of the Academy Software Foundation's Material X project. Thanks to Tobias, Tobias is on the call. He'll be part of the Q&A panel later. He was the originator of that node. And it's been edited by a few other people since then. And it provides a full representation of our material model within the Material X node system. It actually implements it with native Material X nodes under the hood. And this has a number of advantages. The obvious one is if you wanted to import a glTF model into a Material X ecosystem, well, you just take all the parameters and textures from the glTF material, you plug them all into this node, and now it all works in Material X. But the more interesting thing, perhaps, is that it can work the other way as well. If you have a material written in Material X and you can coerce that material to work properly using the glTF PBR node as the final node in your graph, then now you can look and see all the parameters and inputs to that node. Material X has a system where you can bake out all of the inputs to the different parameters on a node, and that will give you exactly the texture maps you would need to put into a glTF file to replicate that material in the Material X system. Also, shout out to Bernard Kwok. He's working on some tooling for us that will hopefully add some more automation to that process and make that conversion a little more seamless. Right now it's more of a by hand thing, but we're working on automating that. So this is one of our newest sample models. This model that we're seeing here, the Academy Software Foundation released as the open chess set at the recent SIGGRAPH 2022 conference. It was originally authored as a tutorial for side effects for Houdini, I guess, and it's really stands as a great example of sort of using the power of the high-end, like USD-driven asset authoring pipeline, and then once the asset is polished and finished and the materials were all designed here originally in Material X, then it can be converted and exported to glTF. And the screenshot that you're seeing here is not the original Arnold rendering of this model. This is a screenshot from 3JS. This is a snapshot of a web page that you're looking at. This model did export to glTF and can be used interactively on a web page. You could make a whole 3JS like chess game out of this and let people move the pieces around individually, even though you can see you've got transmission happening in the heads of the pawns there. So glTF is really striving to be that delivery mechanism that can take a good quality model and not just show you like a real-time preview of it, but really show you a final render in an interactive environment. That was my little dig there, if you caught that. Okay, so I'm going to hand it off to Alex. He is going to take us briefly through some of the fun details of implementing some of these real-time transmission and volume effects. Take it away, Alex.
Thanks, Ed. So in this next section, none of what I present here will be considered groundbreaking, but hopefully for some will serve as a gentle introduction into these techniques. Hopefully we can make them a little bit more approachable. Who wouldn't want to get this very cool macroscopic refraction effect in our renderer? So what I'll do is I'll take us through a walk. I did a frame capture of the glTF sample viewer, which is a Cronus project that we have hosted up in GitHub. And it's designed to demonstrate these materials in a rasterizer. And in our working group, we sometimes will get ahead on some of these draft extensions and might even prototype in and vet, our parameterization using the sample viewer. So let's dive in. Let's get started on the next slide with transmission. So what we're looking at here, we actually saw this sphere a little earlier in Ed's portion. It's the final render of a single yellow transmission sphere. And there is a subtle band of roughness. And we did see that band of roughness there earlier. And off to the right, you see I've extracted out the important bits of the glTF file to see how this material is configured. So most of the surface properties are defined using the glTF 2.0 metal roughness workflow. So the rough transmission parts, those are defined using the roughness parameter that we're all familiar with in the core spec. Now in this simple example, all we need is a simple scalar transmission factor that we're setting to 1 here, as you can see through the KHR materials transmission extension. Now, that extension also defines another optional parameter, the transmission texture. So you can configure that, on across the material on like a per textile level there. And I'll also point out that this being thin-walled, they're typically authored as double-sided being set to true. So in advanced renderers, you'll capture kind of the backside reflections of that transmission sphere as well as the front side. So you have kind of like those two transmission surfaces that show up in the render. Okay, so let's see how this fits into the core material model. Let's go on to the next slide. Okay, so there's 2 parts to this slide. On the top half here, we're looking at a diagram that's pulled right from Appendix B of the core specification. And what it's showing us is how the BRDFs are combined to define that core glTF material. And I'm actually going to focus on that top dielectric box up there. So we have the specular BRDF and the diffuse BRDF that are being combined with that Fresnel mix operator. And then that dielectric and that metal component are combined using the metallic weight, the metallic factor. And I should point out all these building blocks are defined in that Appendix B, and there's sample code, so it really gives you a good understanding of how all these pieces kind of fit together to create these effects. So the bottom portion, we'll look at how we add transmission. We extend this to include transmission. Transmission is defined by light transmitting through the surface, and so our specular surface reflections are actually not affected. If you look at compare these top two renders, you might notice that the specular highlights are roughly more or less the same in both renders. So what we are doing here is we're inserting this specular BTDF, which is controlled by a transmission factor here. So the transmission factor is going to give us a mix between the diffuse BRDF and the specular BTDF, right? So just note the R and the T and those functions there. So the R you're familiar with, the BRDF, that's the bidirectional reflection distribution function, and the T stands for transmission, right? And what that specular BTDF box it's representing, it's an approximation of specular light transmitted through a surface. So there's no scattering of light here. And as you can see, if in that top image, if we had just stuck with the bottom diagram, but set our transmission factor to 0, that more complex material really simplifies back to the original core glTF diagram there. So let's go on to the next slide and we'll take a look at how this is implemented. So as I walk through this frame capture, I've included a high-level overview of the steps required off to the right. And in summary, we're doing kind of what's common for screen space refraction, where we capture this opaque scene into an off-screen texture. We'll map that texture to get all these various resolutions of that. And when we render our transmissive materials, we're going to sample into that off-screen scene. So let's take a look at how this works. So so I'm kind of showing this in the bottom left two images here. You render the skybox and you render all your opaque geometry. And in this case, we just have this checkerboard cloth sheet, and we render all that to the color attachment. Now, you might be wondering why those images are darker. I do want to emphasize that we're capturing the linear light value. So when we sample into this, we want to know what potential light is going to be transmitted through that surface. So as a result, there's no gamma correction, there's no tone mapping done to this. It's just the raw linear light values that we want to capture. Okay, and we do this in a 10 by like a 1024 square texture. We now by having that fixed size, we know the exact number of MIP levels that we have. So it's just a resolution independent off-screen scene here. So let's go ahead and go to the next slide. Okay, so when we're shading our transmissive fragments, we have an interaction at the surface where some percentage of light penetrates through the surface, and that's based on the transmission factor. So we'll sample this off-screen scene and as the approximation of modeling that light that's received from the other side, okay? Now, if you've worked with the core glTF material model, this mapping of roughness to some MIP level should look familiar. We also do this kind of mapping when we're doing our image-based lighting calculation or approximations. It's a similar approach that we're taking here. So these MIP levels that we're looking at here represent the scattering from misaligned microfacets on either side of the thin wall, as discussed earlier by Ed. And so therefore, we need to also make sure that IOR is also influencing that roughness mapping into the MIP levels. So we do that when we're sampling the MIP levels chosen based on a function of both the IOR and the material roughness. And here I've extracted that important line of code from the sample viewer that does that mapping. And really it's holding two things true. One is if IOR is 1.0, there's no setting of roughness that will shift you into those lower resolution parts of the pyramid. You're always indexing and into that top full resolution image or MIP level. And our default IOR in glTF is 1.5. So in that case, there's going to be no additional scaling on the roughness when we're indexing into this MIP tree. So that's what that function is doing there. So let's go ahead to the next slide. So we have our off-screen opaque scene captured, and we've generated our map tree that we're going to use to sample based on roughness. And now we can render the whole scene again, but now we can actually process our transmissive fragments. So that's shown here from left to right. You render your skybox, all your opaques, and you render your transmission fragments. And what's important here is that this yellow sphere, it's not alpha blending. There's no alpha blending going on. You can render it with your other opaques. We're actually sampling this background texture, that off-screen texture, when we're processing those fragments. And so the only thing that's visible behind a transmissive surface is whatever you render into that off-screen scene. One other comment I called out kind of the settings here that we use in the sample viewer. Backface culling is turned off and depth testing is set to true. And that's an approximation that was selected for performance reasons. And as a result, I mean, we are only getting that front surface of processing that front outermost surface of the transmissive material. And alternatively, as I mentioned, right, you could render your back faces to that off-screen scene as well, and then do an extra render pass to capture both sides of the transmission material. This is a thin-walled effect. So in our case for the sample viewer, this is a fine approximation. I think it still carries forward the spirit of the of what the transmission extension can bring. And it's great for common materials such as windows or windshields. And really, that's all there is to rendering transmission. And I think now we go into the next, if we go to the next slide, let's take this one step further and talk about what we have to do to build on top of what we just did to extend this to the macroscopic refraction case. So we'll do that by exploring this dragon attenuation sample model that's hosted up in our glTF sample models repository on GitHub. And off to the right, once again, we see how this material is configured in a glTF material. And so let's look at the important bits right here. So once again, we have the transmission extension that's used, and we're setting the transmission factor to 1, which is enabling light to transport through the material. And the other thing that I've included in here is we're using the materials IOR extension. And that extension is separate from the volume extension. It configures how light refracts through the volume, but it's standalone because IOR does also have an impact on the surface reflectivity as well. And then one other thing I want to point out is that in this sample model, we can see here that I have the IOR set to 1.5. That is the default value. So it doesn't have to be specified here. I just wanted to include it for completeness, just to let you know that it is an important configurable property for the volume extension, or that can be used by the volume extension. But let's talk about the volume extension. So we have KHR materials volume listed here, and this gives us properties that configure the light that survives the absorption, right? As well as some helper properties for defining thickness. And as Ed mentioned earlier, these are important helper. The thickness is important approximations that a rasterizer will use. A path tracer will generally kind of ignore it, but we need that in order to kind of calculate where our exit point is from the volume. And let's see how these come into play in these next few slides here. So let's go ahead, Ed. Okay, so all this should look familiar, right? We're going to, we start by creating that, we use that same opaque scene that we render to an off-screen texture, and we map that just as we did before. So let's go to the next slide. And just as we did before, we're going to render our scene shown left to right, the skybox, the opaques, and any transmission materials, and that includes our volume materials. For the volume material, I guess you should think of the surface as defining an interface into another volume that's enclosed by manifold geometry. So as a result, these are authored as single-sided materials generally. And we really only are going to be processing the fragments on that first surface contact. It's in the shader where we determine the exit point and do our sampling. And sampling is a bit more complicated, so let's explore that on the next slide. So here I've extracted the important bits that are necessary for volume materials on top of what we've already done for that simple thin-walled case. We'll need to use the thickness of the volume and the IOR in order to calculate the UV sample point. And as you can see here, we're using Snell's law to refract a view vector based on that outside IOR. And in this case, the assumption is that it's air, and therefore that's where that 1.0 is coming from. And then it's that ratio of the outside IOR and the inside IOR. And the inside IOR, that's what we define using that IOR, the KHR materials IOR extension. So when we have our refracted vector, we can scale it based on our thickness to find out where we're exiting the volume, and then back that out into a UV coordinate. So once we have our new refracted UV, we sample into the off-screen scene, and that is the same as we did before, just with a different UV. So now we can look up into our off-screen texture and sample the light that can potentially be transmitted through the material. But before we just render that color from that off-screen buffer, we also will be attenuating the light and are going to be left with that remaining light that survived the absorption. We use Beer's law for that. And so you can see here the attenuation color and attenuation distance are coming into play for that color calculation there. And as before, the result of this is all kind of happening inside that specular BTDF box from the diagram we saw earlier. So that's going to combine with the diffuse BRDF and based on that transmission factor. And that's really it. With these additions, we now have support for the volume extension by adding some simple calculations for a refracted lookup into the opaque scene and using IOR and thickness for those two inputs, and then computing the absorption color using those attenuation properties. So just to wrap this up, let's go to the next slide here. So I walked you through two of the more involved PBR extensions that require some extra steps, changes to your render in order to get this working in a rasterizer. We think the glTF sample viewer is a good place to find sample code that communicates the spirit of these materials. And before I end here, I want to point out some crucial resources to help you get started with glTF and with PBR and glTF. So I've mentioned Appendix B a few times in this talk. It's a great resource for starting out with PBR. Thanks to Tobias for really getting that wonderful resource out there. And as you're building this capability in your renderer, we also have a large GitHub repository of sample models that cover a lot of common edge cases that are easily overlooked. There's usually very detailed READMEs that accompany those that will kind of discuss and show screenshots of common problems that you might see in those sample models if you've encountered one of the same issues that we probably encountered ourselves while we were developing these on our own end. Also, I've included here all these properties. They don't just pertain to rasterizers. So Dassault Systems also maintains a path tracing sample implementation that you can go have a look and look to see how this might be implemented in a path tracer. So that concludes my section. We'd like to now open the remainder of this BOF up to a more interactive Q&A. So joining us is a panel of experts that are regular attendees on our Monday PBR calls. Ed, would you mind introducing the panelists?
Sure. So we have myself and Alex. We have Tobias and Bastian from Dassault Systems. We have Nicholas from Autodesk, Emmett from Google, Adam from Target, and Eric from Wayfair. And if it sounds like I'm reading the attendance list of one of our TSG meetings, it's because these folks are all regular attendees and in fact, these folks are some of the folks who taught us what we know about this and helped design these standards and specifications that we've adopted for glTF. So I see people generally have their cameras on, so I'm going to stop my screen share so that we can see the cameras. Yes, if folks have questions, please do use the Q&A button. Zoom has both a Q&A and a chat feature down at the bottom. We're trying to keep all the questions in the Q&A side of this. So diving right in, first question I see here, if I need a certain property not defined within glTF right now, for example, subsurface scattering, and someone else needs that property as well, how do we proceed? Does the lack of standard in a complex properties not create competing extension standards outside of Chronos control whether we like it or not? So it's two questions. These are great questions. I have answers for these, but I want to defer to my Q&A panel since they were nice enough to devote their time to join us here. Who wants to take a swing at this one first?
Honestly, Ed, you're probably in the best position for this one.
Yeah. Okay, so as chair, I guess this falls sort of more or less in my domain. So we do obviously have a draft subsurface scattering extension, and if you're interested in subsurface scattering, we certainly hope that you would be looking at that and testing that. We do hope to have some test models for it before the end of the year sometime to make testing a little easier. But to answer the more general question, what if somebody comes up with a property that Chronos is not paying any attention to and wants to get some more airtime? There are several things you can do. First of all, we do support this thing called vendor extensions. So if you really have a company proprietary thing that you can't even share with Chronos that you need to add to a glTF model, there's a way to register a vendor prefix and make your own vendor extension to hold that property in that file without breaking compatibility with the rest of the ecosystem. If it's something that multiple vendors are all interested in, but that Chronos can't get behind for various reasons, maybe IP or various other reasons, we have another prefix called EXT. And the EXT extension prefix is when multiple vendors want to share an extension, but it's not an official Chronos extension. And it doesn't preclude it from becoming a Chronos extension later. I think we're in a situation now where a couple of EXTs have gotten so popular that they're now on the list to eventually become ratified, and they'll keep their EXT extension because otherwise the software would break. But the Class A first choice, if you have a property that glTF is not supporting and you want it to be a full-blown Chronos extension, come join us in the meeting, right? It's come join Chronos, come join our meeting. If you can't do that, at the very least, give us some feedback on GitHub. We have the main glTF repository out on GitHub. There are issues open, some of which have been open for a while, I will admit. It takes a long time to work some of these things through, but we try very hard to work them through in a way that works for everybody who's using them. But search and see if there's an issue for your favorite parameter on GitHub, and you can leave a comment on that issue. Say, hey, what's up with this? Who's working on this? Some of these issues languish there just because there's no champion. There's nobody really pushing forward, like saying, well, I need to finish these edits to this draft spec and get this the rest of the way across the finish line. Some of them we're just not aware that people are using them or interested in them. Some of them maybe we never even heard of, who knows? Yeah, so find the issue or create the issue on GitHub. And if you can, join Chronos and come talk about the issue with us directly at our Monday meeting. We'd love to have you.
And I might just add regarding like competition between different extensions for doing kind of similar things. I mean, the reality is everyone who's interested in glTF is interested in it specifically because of the universal nature of the support. And most of the popular renderer maintainers are involved with the Chronos group. You know, the most difficult thing that I think that glTF has been amazing at achieving is getting all of these renderers to actually implement full support for these extensions with really consistent rendering. And that happens because there's a lot of trust with the renderer maintainers that the experts involved in Chronos have actually found a really good spec for defining these materials. So I think as a general rule, it is hard for these extensions to get broadly adopted unless they're sort of Chronos ratified, because that is that sort of stamp of approval that says, oh, this is going to be worth my time to implement.
Yeah, and to just add on that, like say that you go and you do create a vendor extension for your own internal use, please tell us about that. Because then when we come back later and we're actually trying to solve this problem for the wider community, we want to actually know which extensions are out there. So we encourage you to get a vendor prefix and then submit a PR with your vendor extension, because that's going to that allows us to give you feedback if we think that hey, there's something that you might want to try different here, or B, it also gives you a chance to actually get it out there, and so people can actually see that you've done something. And a lot of times vendor extensions will end up being what is the match that lights the fire to actually get the entire working group to focus on it. So please let us know about your vendor extensions.
Yeah. All right. I'm going to mark that. Oh, that was answered. Okay. So the next question I have here, this person joined the webinar in the middle and may have missed it. Spoiler alert, they didn't miss it. Is glTF planning to support anisotropy in the near future? So yes, we've had anisotropy on the list, and yes, anisotropy was conspicuous in its absence from my description today. We've had a draft of this extension open for well over a year now. It's currently missing a champion. I like to call these people champions. A champion it's a term I made up, but it's a person usually within Chronos or outside sometimes, who really takes the draft of the extension and answers everyone's comment, like fixes all the little problems and gets it into a state where all the different vendors can really agree, yes, I would want to implement this spec if it were to become ratified. So our anisotropy draft extension has been sitting around with no such person taking care of it. It has a few known issues that we've talked through in the group, and they're all listed out now on GitHub publicly. And we just need someone to come back and put the puzzle pieces together the way they fit and make it go. So long story short, yes, we have a draft of anisotropy. I'm personally really looking forward to the day that it's done. I can't promise when that will be, but if someone's willing to actually work on that draft and hammer it into better shape, that would certainly help move the needle forward on that one. So let's see. Here's another question, and I'm just going to read this. I didn't really pre-read this. I'm just going to read it. General question. I'm at the beginning of my glTF and Vulkan adventure. Awesome. Struggling to reproduce even basic PBR rendering for glTF models in Vulkan using C++. I've been attempting to composite a scene using tiny glTF and Sacha Williams repository at vulkan-gltf-pbr. Can you recommend any other resources I should consult? I find even basic tasks like setting initial position, rotation, and scale is challenging. This is definitely not a question for me, although I like this question. Can somebody else take this one?
I mean, I can speak to some of this at least. I maintain Model Viewer, which is a web component for rendering PBR. It's built on top of 3JS, the rendering engine that really does the work. I've done some PBR contributions there as well. All I can say is I empathize. None of this is easy. 3D rendering, all of this is quite hard, from the matrix algebra all on through the physical transport of light. I would highly recommend making use of existing rendering engines for this exact reason. There are a number of really excellent ones in pretty much every language. Rolling your own from scratch is going to be an absolutely enormous endeavor. You're welcome to. It is great to have more, but like I cannot stress enough that the reason we have open source renderers that we share is precisely because of how monumental a task it was to create them in the first place.
I can add to that too.
Okay. Yep.
Yeah, I agree with Emmett on it is a very hard task. I think I've prototyped these even in toy renderers just for the joy of kind of climbing that mountain. And I've come across a lot of good tutorials. This is not an endorsement from Kronos. This is just my own personal takes that Learn OpenGL is a great approachable resource. The Appendix B in the specification, please have a read, because it gives you source code and shows you how these piece together. And over time, it'll at least get you unstuck and get you some results on the screen. And then you can take later passes to optimize. Then you'll get into more complex things like energy conservation. And there are lots of articles. But once you get that first metallic roughness, the metal rough spheres rendering on your screen, you'll be, I think, ready to take the deeper dives.
Yeah, I'm going to take a swing at this very last piece of the same question here. Find even basic tasks like setting initial position, rotation, and scale is challenging. So glTF does specify an orientation. A proper glTF model will have the positive y-axis is up and positive z-axis is the so-called front of the model. So your initial orientation typically would be such that the camera is pointed right at the model's positive z-axis, or maybe at some artistic offset from that, 30 or 45 degree offset from that, perhaps looking down a bit, perhaps looking straight on, your choice. The other thing I found is that most viewers will go through and figure out the overall bounding box of the model and center the camera on it. Not all of our sample models are centered right at the origin for one reason or another. They come in different sizes. They might be placed here or there away from the origin. Most of the sample viewers that are out there will calculate those sizes. And glTF has a min-max bounding box thing happening in the accessor data structure. So you can figure out the extents of the model and zoom your camera appropriately to start with, and then give the user control from there. So hopefully that answered your question.
One other thing that I want to just add, we do have a Slack, a glTF Slack, and at least for glTF questions, that can be a useful resource once in a while. There's several people there who are very open to answering all sorts of questions.
Yeah, that's a good reminder. Can somebody put the link for that in the chat?
Yeah, let me find it.
And as already mentioned, our GitHub org, we link to a bunch of resources there, and there is plenty of information there.
And if you're looking specifically for a C++ based renderer, I might recommend Filament. It's another Google open source project, and it does a really excellent job both in making performant rendering, but also in documenting exactly how they chose the approximations they did. I think a lot of us have learned a lot from that documentation over the years.
Yes. Yeah. So I see one more question here about how many viewers support extensions like transmission. We've got a bunch of them. Model Viewer, of course, 3JS, Babylon.js, the glTF sample viewer. I can't say enough about the sample viewer. If you're really trying to learn this code and understand how these different parameters work together. The sample viewer is open source on GitHub, and it really is meant to be this learning resource where you can see how the sample implementation of these things are done, at least from the rasterizing point of view, not as much the path tracing side of it. Yeah, I forget. Are there other? I'm sure I'm forgetting dozens of implementations. I mean, Blender can import it. Autodesk, I believe, can import it into 3D Studio Max. Let me know if I've forgotten any. All right. So do we? I think we've got through most of our questions here. Do we have any other questions? I'm developing a WebGL library. I'm struggling with how to verify the correctness of the lighting with each new extension that needs to be supported. I would appreciate a way to check the correctness of each element of the writing step by step. Yeah, lighting can be a tricky, Emmett's grinning as he knows lighting can be a tricky situation. It's as we've discovered, some would say the hard way, it's very dependent on the environment. Your model, even if it's just a diffuse couple of colors, it can look so different depending what lighting environment you put it in. And it's very hard to be certain of that. That being said, we do try to lay out the math in our specifications such that there's not a lot of wiggle room for making up your own colors and such things. Let's see. I don't know. Emmett, you have?
I mean, one thing I can say, we on our dev site modelviewer.dev, you can go and check out our page on glTF fidelity comparisons. We maintain this as sort of a benefit to the glTF community at large, but also to ourselves. So it renders not only the sample models via our own renderer with 3JS, but also the most popular web renderers that we can find, Babylon, Filament. And we even have Dassault's path trace versions in there as benchmarks. And I think that's really important because, again, having worked on all this lighting for a long time, I can say that everything a rasterizer does is very approximate. And we do our utmost to improve those approximations. But the nice thing about the glTF spec is it doesn't say this is how to make your rasterizer shader run. It tells you this is what physics is supposed to represent. And so you can go through with a path tracer and do things very slowly and carefully and get very clearly what the right answer is. And Dassault does a pretty decent job of that. I'm sure they have approximations too, but they're pretty solid. And then there are things that rasterizers just have no way to do right now performantly, but mostly we can do pretty well. And you can look through those fidelity tests and look at all those images and kind of see how close everybody is. And we use that all the time for filing bugs. I mean, those images used to look a lot more different than each other. And over time, they have come together as we filed bugs and said, oh, wait, it looks like this renderer's approximation isn't doing this part right, or this other one is having an issue. Anyway, that's all open source. You're welcome to add your own renderer in there, but it might actually be more useful to basically fork that source and be able to basically run those comparisons yourself on your own code. It may be beneficial in learning. We have a config file that allows you to set up lighting and camera angles and all that kind of thing, so you can test a lot of different things fairly rapidly.
All right. Well, okay.
Ogling can also be useful. A lot of the viewers support ogling various extensions and other features through their consoles.
So we have another question that came in does Cronus endorse specific production pipelines? I'm a game developer. I've spoken with a few colleagues about GLTF, the GLTF workflow. And at our studio, we're currently using Filmbox as the main extension, but I'm interested in using GLTF as our main extension. My question is if anyone on the call has heard or worked with GLTF in game engines, and what are the upsides and the downsides?
I could take this.
Sure.
It really depends on what game engine you're working with. I would say if you're working in an engine such as one of the WebGL based engines, such as Babylon.js, or a homegrown kind of engine type thing written in 3JS, or Google's model viewer, GLTF is very, very easy to work with in those engines. When you and I also want to call out Godot as well, although they're not really HTML, but they're also a really, really good candidate for using GLTF. When you get into some of the other engines, such as Unity and Unreal Engine, and so at Target we use Unreal Engine a lot, it gets a little tiny bit more difficult if you're trying to do it at runtime. If you're just trying to do it at kind of, I guess, build time, it's not any more difficult than any other asset. It actually works pretty well, at least in the case of Unreal Engine. And last time I used Unity, it worked very, very well there too. Where you get into troubles with those engines is it gets a lot more difficult if you're trying to pull them in at runtime. In terms of Unreal Engine 5, there is now a really great extension or plugin that is, the name of it is escaping me. I think it's called GLTF Runtime. And it's open source, and it supports most everything with GLTF now. There were some kind of extensions that it was kind of not supporting at first, but they have an Epic Mega Grant, and they're trying to catch up, as far as I am aware. And then I forget which, maybe somebody else on the call knows, but I forget which plugin for Unity right now is the main one that we recommend. I know there was GLTF Fast, but I don't remember if that was the one that we recommend these days. So
I don't know if we
and I can
officially
add to
recommend
that
them.
too.
well, that's true, yeah, but
Like if you want to use GLTF as kind of a translation format to supplant FBX, for example, that you mentioned, I mean, it's great because it supports PBR right out of the box. And so you get a really nice formatted material that's easy to load in a lot of different tools. And so GLTF is really strong at that. But as mentioned before by Ed and Alex, it's really it's meant to be a transmission format, and it's meant to be like final delivery. So often the contents are compressed or lossy in a way. You can get around that by using non-lossless texture formats like PNG and not using mesh compression. So then it just becomes a container and you can use it that way. It's just not kind of the official supported idea because it's really meant to be a transmission format, but people definitely use it as a translation format, and you can certainly do it that way.
yeah, it's worth mentioning, at least in our pipeline, we do still work with Filmbox. We also work with Alembic, and we're starting to work with USD. And then what ends up happening is when we finally get to the point where we're actually going to be serving up to the user or something, we do everything real time. So we end up putting it into a GLTF and serving them up that way. So if you're worried about like the artist side of things, I would really kind of steer you, as Eric said, I would steer you away from that as well. It's really for that kind of final delivery that GLTF really shines.
Awesome. Okay, I think we reached the end of our questions here. I'm going to share the one last slide. So if you want to catch the recording of this later, it's going to be up on kronos.org/events. That is our webpage where we will host this, and the video of this is going up on YouTube. If you're watching the YouTube recording, smash that like button. No, I'm just kidding. I watch YouTube with my kids, and they see that all the time. Just gently click on the like button. That will do fine. Yeah, thank you all for joining, and we hope you learned something today, and have a great day. Thanks.
Thank you, Ed. And thank you all to all our presenters and panelists today. We appreciate your time. As you leave the meetup, please take a moment to fill out the survey that pops up. Your feedback is important to help us improve these presentations. Please let us know if there are other Chronos-related topics you may be interested in. And thank you for joining us. We hope you enjoyed the meeting and have a great day.